So in this video we're going to be going over some more related rates. So in this example it says, assume that the radius of R of a sphere is expanding at a rate of 14 inches per minute. The volume of a sphere is V equals 4 over 3 pi r cubed, and the surface area is equal to 4 pi r squared. In this example is right here. It says, determine the rate at which the volume is changing with respect to time when R is equal to 8. So we're trying to find the volume. So we know volume is equal to 4 over 3 pi r cubed. We're trying to find the rate at which the volume is changing. So we're going to go the derivative with respect to, we'll take the derivative with respect to x of all this. So it's 4 over 3 pi r cubed. And this is going to give us our derivative of volume with respect to time of 4 over 3 times 4 over 3 pi. We'll go like this. 4 over 3 pi over 3 pi times 3r squared dr dt. So that's what we get when we take the derivative of that. That's just going to give us, if we just simplify this, so we're just going to multiply the 4 and the 3 across, it's going to give us, we're just going to do that over here, so it's going to give us dv dt is equal to 12 over 3 pi r squared dr dt. And this is just going to simplify to 4, so it's dv dt is equal to 4 pi r squared dr dt. That's the equation we're going to use. So we know the radius is equal to 8 inches, and we know the radius is expanding at 14 inches per minute. So now we just pretty much just plug and chug now, so it's just going to plug that into our equation. So we're finding the derivative of volume with respect to time, because that's what they said, because we're trying to find how much the volume is changing with respect to time, because that's what was stated in the example problem. So now we're just going to plug things in. So it's 4 pi r, which is equal to 8 squared times 14. And that's just going to give us, we'll just do that up here, so we already know all this. dv dt is equal to 35,084 pi inches cubed per minute. And that's going to be the final answer. For that. So the volume is changing at a rate of 3,584 pi inches cubed per minute. So now we can do another example problem. Let's just erase this real quick. So now the next problem is going to say, determine the rate at which the surface area is changing when the radius r is equal to 8. It's pretty much the same idea, except we're going to be using the surface area equation. We know surface area of a sphere is equal to 4 pi r squared. So now we're trying to find the rate at which the surface area is changing. So we're going to take the derivative of all this, and that's just going to equal the derivative of area with respect to time is equal to 4 times 2 pi r dr dt. And that's what that's going to equal, and take the derivative because you're going to be using the power rule on the r squared, and that's going to move in front of the whole equation times 4. So then that's just going to give us 8 pi r dr dt, which is what the area equals, dA dt equals. So we're just going to write as a side note, r is equal to 8. So we're just going to erase all this real quick. So now we have our equation, dA dt is equal to 8 pi r dr dt. So now we're just going to solve, because we're trying to find how much the area is changing with respect to time when r is equal to 8. So we're just going to write dA dt is equal to 8 pi r, which is equal to 8, dr dt, it's stated in the beginning of the problem, is 14 inches per minute. This is 8 inches. And this is just going to come out to equal, so dA dt is going to equal 896 pi inches squared per minute. These units come from multiplying all this, and you get inches times inches, which equals inches squared. Then just the minutes go across as well. And that is your final answer for that one. So this is the related rates for spheres, pretty much. So we used the information given to us to find the area, and we solved for the how much the area is changing with respect to time. And that should be pretty much it for these two problems.